Hello Chem 1A, this is Chapter 1, Lecture Video 8, and this is our last lecture video for this chapter. In this chapter we're going to be talking about accuracy and precision as well as scientific notation. So, scientific notation, hopefully this is review, involves a number between 1 and 10 multiplied by 10 to the power of some value. It allows us to express really large numbers in a shorthand way or really small numbers in a shorthand way. This is generally the setup of a generic scientific notation. Now, one of the important bits is this number here only contains significant digits. So you can't contain numbers that aren't significant. In that number, you don't record them in scientific notation. And in addition, you can't leave off digits here that are not significant as well, or that are significant. So let's write some numbers using scientific notation. So when we're doing this, the way we do it is we have a decimal here that we're not showing, but we need to move that decimal so that we get a number between 1 and 10, which means I need to move the decimal here. This will give me 9.54, and then I multiply that by 10 to some power. Now the exponent that I use with the 10 depends on how many digits I move my decimal, and also depends on which direction I move my decimal. So I'm moving the decimal to the left, and I'm going to count how many places I moved it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because I moved it to the left, I know the exponent's going to be positive, and because I moved it 11 places, the exponent is 10 to the 11. I then add my units at the end. This would be 9.54 times 10 to the 11 atoms. If I want to do a really small number, I can do that as well. This time we have our decimal here. We need to move it to here so that we get a number between 1 and 10. So 5.47 is my number between 1 and 10. I have that multiplied by 10. I need to figure out my exponent. So I need to count how many places I'm moving it. Now I'm moving it to the right, which is going to make a difference. 1, 2, 3, 4, 5, 6, 7, 8, 9. This means I have an exponent of 9. But since I moved it to the right, I need to put a negative sign in front of my exponent. This is 5.47 times 10 to the negative 9. And yet again, I got to put my units of grams there. We're all set. Okay, let's talk about experimental error. We can use two different vocabulary words to describe error in an experiment, and they mean different things. Precision and accuracy often get confused as the same thing, but they are not. Precision is how well repetitions of the same experiment agree with one another. This means if I'm getting the same number every time I do the experiment, I am very precise. However, accuracy means something different. Accuracy is how well that measurement agrees with the correct value or the accepted value for my measurement, right? I can be very precise but not accurate. I can be very accurate but not precise, and we need to understand the differences between that. So let's talk about a dartboard analogy to do that. We want to hit the bullseye, right? I want to hit right in the middle here of this bullseye every time if my measurement is perfect. Both in precision and accuracy, I want to hit it over and over again right in the center. Now, for the sake of measurements, generally when we do repetitions of the same measurement, we take the average measurement to determine accuracy. So we're going to take the average positional point for these darts that we've highlighted in yellow, and I'm going to say that the average of these 4 darts would probably be about right there. This tells me that this measurement is not accurate and not precise. How do I know it's not precise? Well, because none of the darts landed in anywhere near the same location. And in addition, we did not hit the bullseye for our average point of position on the dartboard, so we weren't very accurate either. This is kind of, I would say, the second worst scenario. Usually what this means is you're not taking into account something in the experiment, or you're doing the same mistake or different mistakes each time you do the procedure. Here we have another dartboard, and as you can see, all our darts are grouped in the same location. Now that location is not in the center of the dartboard, so we were not accurate, but we were definitely precise. We have this cluster all in the same area. We are hitting the same answer every single time. This usually implies that either you're doing the same mistake with your procedure every time you do it, or the procedure is missing something that is causing all your answers to be off from what you'd expect. Finally, we have accurate but not precise. If we look at the average of these 4 dots, our average is dead center in our bullseye. But these are not precise. They are accurate because we're averaging them to get our accuracy. However, this is the worst case scenario because this is deceptively accurate. If you are not hitting the same number every time, there is a problem with your experiment. And just because your answer averages to the correct value doesn't mean your experiment actually went well. This can cause confusion and misleading data, which is kind of the worst scenario in my personal opinion. If we had our way every time, our goal is always to be both accurate and precise. We want to hit the correct answer every time, over and over and over again, or at least close to the same answer every time, and that answer to be very close to the correct accepted value. Now, how do we measure or calculate error in our measurements? Well, first we take our experimental value, usually the average, by the way, minus the actual. However, if we only take one measurement, then it would just be that one measurement. Otherwise, we always use the average experimental value minus the actual value to get our error in the measurement. This is not very valuable, as it doesn't take into account the actual numbers that you're working with. For instance, if my experimental average was 1 million and the actual value is 1,100,000, it would look like my error in this measurement is 100,000, which might seem very large, but since the magnitude of the numbers is so big, it's not actually that big of an error. We use percent error to usually quantify error in our experiment because it gives us a more realistic understanding of how inaccurate we actually were. So we take the error in our measurement, this guy, and put it down here into this equation. We take the error and we divide by the overall actual value. That times 100 gets our percent error. And this is a much more accurate measure of how inaccurate we were, which is a funny way of saying that. All right, so let's do a problem. A student runs an experiment, gets the following results for the density of water. Is the student precise? Is the student accurate? Let's calculate the percent error. So we know, hopefully, that the density of water is 1.00 grams per milliliter. And if you didn't know that, now you do. That's a number you should know. Now, based on that number and these values here, I can't really tell if the student is accurate until I calculate the average and measure my percent error. However, I can already tell whether the student is precise. As we can see, these numbers vary greatly from each other each time, with the exception of these two. These two can kind of be considered precise, but overall, these numbers are not precise. This student was not precise when they did their measurements. Let's determine the average value here. So the first thing we're going to do is we're going to average our values. So if we calculate the average of these 4 numbers, we get 1.01 grams per milliliter. Now, using this value, we take our average experimental value minus the actual for our error measurement, right? But our percent error is going to be equal to 1.01 minus 1.00 divided by 1.00 and then multiplied by 100. Again, this is the experimental average minus the actual divided by the actual times 100%. This will give us a percent error of 1%. And if we look at our subtraction, again, sig figs are important. We subtract these two values, we get 0.01. This has one significant figure. When I divide this value that has 3, this is an exact value, a definitional one. We should only have one sig fig, i.e. our answer is actually 1% exactly. Now, this I would consider to be pretty low percent error. Generally, if we're under 5% error in chemistry, that's good news. Okay, so this ends chapter 1. If you have any questions, please feel free to ask. I'm always happy to help, as always.